Okay.
Microphone check done. You ready?
Yeah.
All right. Well, take it away, Ezra.
Okay, thanks. I'm Ezra Cooper. Welcome to sunny Seattle. I work at a place called the Institute for Health Metrics and Evaluation here in Seattle at the University of Washington. This work was done alone, but I am looking for a collaborator. So if this sounds interesting to you, please find me during the lunch break or elsewhere. And this is about a surprising connection that I found. Maybe that's disingenuous because all research is about surprising connections, but most of what I have is just the surprise and a little bit of actual results, but it's work in progress. So it's a story of some three roads converging. I'll explain what all these are, but this audience is probably most familiar with algebraic effects. There's another line of work called RPO, and that's from rewriting theory. And then the third line is whatever your rewrite system is, and it's inspired by a particular rewrite system that I worked with. So I'm going to talk a little bit about the rewrite system that I started with, but I think the more general results are in unifying kind of rewrite theory with algebraic effects. So to make it concise, I claim that the meta-language for algebraic effects makes a good target to extend other rewrite theories. And I've been working on this thing called the recursive path ordering, but that's really just one application of the idea. Here's kind of the history of these different roads. I think it's kind of interesting to see the pace at which they all unfold. My particular problem is called NRC flattening. And you can see where I wrote a paper here, and other people have been continuing that work. Of course, algebraic effects kind of started with Plotkin and Power in 2001, and rewrite theory has a long history. And I'm particularly using these papers, but drawing from something much older. So it's just a case study in how research lines can foment and contribute to one another. I would say these are kind of three totally different communities. I haven't heard people talk very much about rewrite theory as such within programming languages. So it's a convergence. There's kind of showing, this is sort of the same picture zoomed out a little bit and looking towards the future. So I was trying to solve a translation problem in a compiler, in the Lynx compiler, and an easy way to solve that problem was by giving a rewrite system. There are other ways to solve it, but I found myself using a rewrite system. There's a body of work on rewrite theory. A lot of work went into proving termination of that rewrite system. 2 years for a rather dull PhD student. So the paper proof was 20 pages and very hard to check. Very hard to produce and very hard to check. And in fact, there was a flaw. Someone found a non-trivial flaw in my 20-page proof. And they had to go and write another 20-page proof that recapitulated a lot of the stuff that I had said, but added more material to fill the hole. So that's a pretty inefficient research process. Wouldn't it be nice if there was some more general theory that we could use to solve problems of this type? And at last, I can sort of claim a shorter, more general proof of termination for a class of rewrite systems similar to my original one. And that, loosely speaking, that class of systems is the algebraic effect systems. I still have a lot of restrictions on my results, so that's why it's a work in progress. I don't want to talk a whole lot about the motivating example, but I think it's interesting to see kind of where the spark came from and maybe why this wasn't obvious in the first place, or maybe it should have been, I don't know. So my motivation was talking about flattening nested data queries. So I wanted to take general program code from programs and extract it and translate it to SQL queries. The general program code used list comprehensions or bag comprehensions, and it allowed nested data as intermediate data structures. SQL does not allow that. So that was the motivation for doing some kind of an interesting translation. I did it using this rewrite system. This is, you really can't read that, can you? But it's sort of meant to show you, this is sort of the rewrite system that I came up with. It has a whole bunch of rules in it. You know, the implications of using this rewrite system were maybe not obvious. And termination was maybe not obvious. I mean, it took 20 pages of incorrect proof to show that it terminated. So so there's a problem to solve here. In the literature on term rewriting, they always give example rewrite systems. And can you prove this is terminating? Well, here's one that arose organically and has its own little quirks, right? So some highlights. So I labeled this meta language, and you'll see why later. But first of all, this is a rewrite that takes. So the language has list comprehensions or bag comprehensions, which are written for x drawn from something, and then it has a body. So for each of these things, evaluate that expression and collect them all up into a result. And this rewrite rule says that if you have a union in the subject of that for comprehension, you can extract the union out. You have to duplicate the for comprehension. But this gets me closer to my result. I claim that this helps me translate things to SQL queries. And likewise, if I have an empty set in the source, I can rewrite that to just an empty set. The n goes away. The whole thing is empty. So these are kind of like equations, but they're oriented because I believe that these are getting me closer to some goal. So it makes a kind of operational way to interpret the equations that you might have in an effect system. As effect systems are often presented. So I call those meta language ones. Here's another example of a rewrite rule that does not involve the for comprehension. This is a rewrite between symbols, so the u plus symbol and the empty set symbol somehow interact, and I can rewrite that to something else. And that's a symbol rewrite. I'm going to call it sort of an effect rewrite, and you'll see why in a minute. So where I start to make progress is by observing that the rules in the top category are sort of meta-language rules. They're part of the broth, and the symbol rewrites are the soup of ingredients that you bring as a user. So let's go from broth to soup. So the broth is the meta-language. I'm going to say that it has this grammar. We've got variables, function applications, function abstractions. We have a let form, which is it's sort of a do notation from Haskell. It's a monadic bind. And then we have effect symbols, which I'm using very old notation here. So this is going back to kind of the original Plotkin and Power stuff. The effect can take some parameters, which is some kind of data that you're supplying to it, and then it has these continuations. The T terms are continuations. So that's not the modern kind of way that you see effects presented, but it's useful for the problem that I'm trying to solve. So that's an effect that takes some data, and it will continue on one of those terms depending on what sort of output it wants to return. We have these rewrite rules, which are pretty standard. We've got beta reduction for lambdas and applications. We have beta reduction for the let forms. I have a type distinction between values and computation. So pure is like return. It lifts values into the computation type. So if you have if you're letting x be a pure computation, we can beta reduce that. This rule is let association, so it sort of linearizes your let statements. And the last one is maybe the most interesting. This says that if the subject of your let is an effect application, we can lift that effect application out of the let, and we have to duplicate the continuation u. So if the effect has many continuations, this vector here represents for each ti, we say let x be ti in u. And so this is kind of a slightly different form of what you see in the original Plotkin and Power paper, and it's stated in just about that form in Plotkin and Pretner 2008. And I'm making such a fuss about where it appears because this is actually equivalent to this rule here. If I think of the u plus as an effect term with two continuations, this is one of those operations. So this appeared a long time ago, but I didn't see the connection. Some technicalities. So I'm using a simply typed setting. I have no fixed point combinator. I'm trying to show termination, and so I'm explicitly ruling out recursion. And computations have a computation type, as I mentioned. And this is a slight extension of the system shown by Lindley and Stark to be strongly normalizing using top-top lifting. This rule does not appear, but these other ones do. And the lead association was one of the difficulties that required the top-top lifting approach. So that work is very relevant, and I'm adding something to it. So that's the broth. To solve your particular problem with your particular rewrite system, to do interesting things with your rewrite system, you need to bring your own vegetables to chop up and throw in the soup. So you bring your own rewrite system, which for now has to refer only to effect terms. So you can't refer to abstractions, you can't refer to lets. But you can give rewrites on the effects themselves. And here's an example. This is a very standard example from algebraic effects. This is global state. And I'm presenting it as a rewrite system rather than as a set of equations. The things on the right each have one fewer symbol in them. And this makes progress in some way. OK, we've got our soup. Sit down for the meal and get some results. So my claim again is that the meta language for algebraic effects makes a good target to extend other rewrite theories. So you've brought your rewrite theory. I want to show, for example, that given your user relation, you are the user, you bring a rewrite system with its own effects. I want to take the union of that with my meta language and show that combination is strongly normalizing. And in general, even if your effect system like this, it's easy to see that this is strongly normalizing. But as a proof, you don't get that for free. If the meta language is strongly normalizing and the effect system is strongly normalizing, it's not necessarily obvious that the combination is also. So there's no such guarantee that this combination will be strongly normalizing, but there are some good standard techniques for showing normalization. This may be a little bit out of order, but some related work that solves a very similar problem, Donald Lehmann and Sam Staton, use almost exactly the same language, and they allow arbitrary effect symbols, which have their own interpretation. And they have a rule that commutes effect operations out of evaluation contexts, just like I do. And they show normalization by evaluation, which is one way of normalizing a term. I was still interested in applying this general body of rewrite theory and things like strong normalization, which shows that any way you apply the rewrite rules will succeed, will reach a normal form. I think that's kind of intellectually interesting, and maybe it has some applications if you don't want to implement normalization by evaluation, but you want some compiler or interpreter to apply rewrite rules in some other fashion. It may be useful to know that the rewrite rules are strongly normalizing. So that's really the setting, which I think is already kind of interesting, is to say that rewrite rules between algebraic effects plus the meta language is a setting in which to do some further research. The particular thing that I'm doing is trying to extend RPO to algebraic effects. When I first published my paper, the reviewer said, why this proof? Why couldn't you just use HORPO? HORPO is the higher order RPO. And I said, oh gosh, I must have missed something obvious. So I looked and I studied the HORPO paper and I went over it and over it, and I couldn't make it work. And I have a good reason why that didn't work, but it seems like it should be possible to extend HORPO in some way to handle this meta language. And that's where I'm trying to get to. That's where we'll get to by the end of the talk. So to lay a little foundation on the term rewriting side of that road, let's talk about term rewriting systems. You can show termination in many ways. You can use counting arguments where you assign a metric to the terms, and you show that the metric of each left-hand side of a term of a rewrite rule is greater than the metric on the right-hand side. Those would be numerical metrics. There's simplification orderings, and there's this thing called RPO. So I want to explain RPO because I think it's kind of interesting, and it's something from the term rewriting literature that is probably not familiar to everyone, and also because I think it will actually be a useful tool here. Here's an example rewrite system. We could show this to be strongly normalizing using a counting argument, but it's a simple example I can use. It's a fragment of piano arithmetic, right? It says if you add the successor of something to something else, it's just as good as if you added that thing to the successor of the second thing. So it makes progress by moving the successors to the right. And if you add 0 to something, you get just t. That's a little example that we can walk through. So RPO comes from Nachum Dershowitz in 1982. It's a nice little paper, very easy to read. And it's one technique, but it's a pretty powerful technique for showing systems to be normalizing. It works on a lot of things that counting arguments wouldn't work on. So it defines a relation, which I'll use this curly less than symbol. The client, that's you, gives a signature of the various symbols in your rewriting system. And you have to order those symbols. So you have to do a little bit of work. You have this finite set of symbols, and you have to order them. And you need a little intuition for how to do that, or you play around with it until it works. In my system, there's like 5 different symbols, so it's not too hard to work out an ordering on just the symbols themselves, not the whole terms, the symbols. In this example, we can just set add as greater than successor, because the left-hand sides tend to have add as the head, and the normal forms tend to have successor. So RPO says, given that ordering, you now need to check all your rules to see that they meet these criteria, and you get to play a little bit of a game. There's 3 different moves you can make. You look at the right-hand side. You can either skip the head symbol on the left and just recurse to a child, so sort of finding it as a subterm, or you can compare the head symbols. If the head symbols decrease going from left to right, then you have to check the arguments in a certain way. If the head symbols are equal, then you have to check them in a slightly different way. I think it's easiest to show them this way. In the RPO literature, they don't use horizontal lines at all. There are no horizontal lines. But I think this is actually a pretty clear presentation. So if we say that S and T are terms headed by some effect E and some effect E prime. By the way, I'm going to say effect when it could just be an arbitrary symbol. Effects are the particular types of symbols we're working with, but in RPO it would really just be any symbol. So those terms have whatever arguments they have, and if T is actually, well, if we want to skip the head symbol and just compare T to a subterm, we can do that. That's a move. Otherwise, we've got to compare the head symbols. If the head symbols decrease, that's fine. We still have to check that all the arguments are less than the whole term on the left. If the head symbols are equal, then we have to check that the arguments are lexicographically decreasing under this same order. And we still have to check that all of the arguments on the right-hand side are less than the whole left-hand side. So with the lexicographic ordering, you could have your last item could blow up, but that's not allowed here. So that's actually pretty concise and relatively easy to check on a given system. I worked through a whole thing here. And I guess I'll just go through it so that everybody sees it. So I want to check that this rule given earlier falls in the RPO ordering. So I claim this, and it's by 2 through 5. So I'm going to use the rule that compares the head symbols as equal. So add is add. And then I have to lexicographically compare those arguments, which works because S is less than the successor of S by the subterm principle. And then I have a second obligation. I have to check that all of these arguments are less than the whole left-hand side. S is less than the left-hand side because it's a subterm. Successor of T is not a subterm of the left-hand side. But I can still solve this problem by using another application of one of those rules. Add is greater than successor. And now I just need to check that all of these arguments are less than the left-hand side, which they are by the subterm rule. And in a way, you can see why it's called recursive path ordering, because I'm somehow finding a path through the tree on the right-hand side and matching all those symbols to a path on the left-hand side. And I can skip nodes, or the nodes have to be kind of less in some way. So I think that's kind of a neat trick. So we'd like to now extend this to higher order. So the original RPO didn't allow any lambdas or lets. It was just purely talking about symbols, term symbols. HORPO came many years later, and it extended that with lambda and application, but it has a bunch of side conditions, a bunch of restrictions. So my work is I'm inventing, I guess, LARPO, the let-aware RPO, and it's going to allow let, lambda, and application, but I still have some restrictions, so work in progress. The first question is, why can't I just use HORPO directly? After all, maybe the let form is just syntactic sugar for a lambda in application in some way, but it doesn't work. HORPO has all these restrictions. Basically, none of the rules you want to use go through. The let assoc rule, for example, reorders lambdas in applications in a way that it does not allow. And that's actually not surprising at all, because HORPO used some strong sauce, and the top-top lifting approach is an even stronger sauce. So RPO used, the proof was by the Kruskal tree theorem, which I don't know exactly how that works, but it's sort of a discrete math theorem. It's sort of a graph theory thing. HORPO did something that I'm calling a stronger sauce. It uses Tate-Girard reducibility or logical relations. And somebody, I think, later today is going to talk about showing normalization in effect systems using a logical relations proof. So I might get scooped even later today. But when we have the let form actually presents some new challenges, as we saw with this Lindley-Stark proof, which used top-top lifting. It's a new proof technique. And when a new proof technique is needed, well, either it wasn't needed or you're going to need it every time you're in a similar situation, right? So it's no surprise maybe that HORPO doesn't smoothly handle the let form. So top-top lifting is a whole nother technique that could maybe be a fourth branch on that original roadmap. But you can stamp out the proof and expand it a little bit. And you need to accommodate effects commuting out of evaluation contexts or the subject of a let. So there's some extra work to do there. And then you have to integrate sort of the RPO proof, the way that all of these rules, you need to integrate those into the proof. But that can be done. Where did I get to? And so that's the success story that I have today. But it does still have some limitations, and I can't solve my original problem of that NRC flattening. HORPO does allow you to have some interactions between your symbols and lambdas. And in my NRC case, I had a very unusual thing, which is that the U plus operator can appear in the body of a let, and I allow that to rewrite out to the outmost thing. You wouldn't have that in a typical effects situation, because that amounts to reordering your effects. The E here has jumped ahead of any effects that might be in S. So that's a little bit strange. But maybe that happens if you have effects that are commutative with all other effects. So the connection with algebraic effects still seems to connect. I said remember the troublesome rules, but I cut that part of that slide, so you haven't seen that. Anyways, I want to allow the client to bring rules like that interact with let, and I don't have that yet. The quest is not yet over. Right, so I moved the slide here, right? So this is a piece of my original slide that shows rules that do work under this framework and rules that don't yet work. So yeah, it's work in progress. I do think that the algebraic effects meta language is a good setting to extend existing work. And I'm pinning down, or not pinning down, a specific meta language. I mean, my work is actually using this formulation, which is, it's not fine-grained call by value. It's very general. It's allowing arbitrary terms in lots of places. And that works for me because I was doing this work with a kind of source language, and I wanted programmers to be able to put expressions wherever they want to put things. So I'm quite happy working in a fairly general meta language. But just generally speaking, having let in your language and involving that with rewrite theory is what I'm calling the algebraic effects meta language. So back to the end here. We have a basic proof combining top-top lifting and RPO. We do have some restrictions, no user interactions between operations and let, beyond what's actually specified in my meta language. And I'd love to collaborate with somebody, so if that sounds exciting, email me at ezra@ezrakilty.net or find me at the conference. So, this is a little teaser. So these are some specific things that I still want to do. Allow rules to use let in more ways. I'd like to play around with a non-specifically typed computation type. Find more use cases. So I've got this one weird case of NRC flattening, but maybe there are other cool examples. Formalize it in Coq. And actually, the holy grail would be Mitsuhiro Okada has a proof from the 80s that you can take any terminating symbol rewrite system and combine it with lambda, and you still have a terminating system. So he doesn't rely on a particular technique like RPO. He says any terminating symbol system can be combined with lambda. So it would be neat to show that you could do that with let also. So now I'm ready for questions.
Let's thank the speaker. All right, I think we have plenty of time for questions. Yes, we have a question. Ohad, welcome over.
Thanks. I have a short comment and a question. So, RPO, Dershowitz about RPO, his history is with the multiset ordering. So that's like
Is with the what?
Multiset ordering, the Nahum.
Yes, that's
the
correct.
Mana Dershowitz.
That's right.
So that's like a superficial connection with queries because the model for queries is multisets. But that's just a superficial comment.
Yeah.
So
I use lexicographical ordering here. You can use the multi-set ordering also, and you can actually use both. In the HORPO work, they allow the option on a symbol by symbol basis. But yeah, go ahead.
No, proper question. So you want to combine arbitrary rewrites on the algebraic side with the theory of let, right? But you don't have a proof, that's fine. Do you have any counterexample when this is not okay, or do you think it is okay, you just don't have a proof?
Yeah, so do I have a counterexample where it might not be okay? So the HORPO rules are sort of restrictive. For example, they only allow you to compare left and right sides where both are headed by a lambda. I mean, if either one has a lambda, the other one sort of has to have a lambda. So that's pretty restrictive, unless you're actually using the subterm case. That does suggest that there probably are some cases that don't work, some restrictions that will always be needed. But I think that all of the rules in my system can go through. It doesn't seem like let gives you a new opportunity for recursion. So, and it's not a recursive let; it's a non-recursive let. So, yeah, I think that it ought to go through. That's my intuition. Yeah.
All right. Any further? Yes, Sam. Come over here.
The very general result of, who was it, Okada?
Yeah.
What is a rewrite system in this setting? This is just first order rewrite rules?
That's right. So it's a set of symbols that have arguments, right? And the rewrite rules would use the leaf symbols, the leaf variables in some other arrangement with some other symbols above them. So it's very much a first order thing. You can't define beta reduction because you don't get a substitution function there. Right.
I see. So the idea is basically you have a pretty powerful kind of. Oh no. So that's sorry, I got that wrong. You have a binding structure with let.
I do.
No, in this
Okada
result.
doesn't, but I do, yes.
Oh, Okada doesn't.
That's right.
Right. Oh, but he had lambda.
Right.
Yeah. So okay, you have a fairly powerful higher order system, but that's fixed. And then on top of that, you have a very restricted first order.
Exactly right.
Yes, all right. And you're trying to do the same thing in a slightly richer setting.
Right. Just by adding let to his system, basically.
Yeah.
All right. Any further questions? Yeah. Oh, yes, we have one.
Just a quick kind of vague comment, but I've talked to some people who are working on Curry, the functional logic system, and I'm vaguely aware that there are scenarios in a functional logic setting where let cannot be translated into a lambda, and that seems like it's potentially relevant here, that you have some meaningful difference between adding lets and adding lambdas.
Yeah.
But that's the extent of the comment.
Cool. And you're alluding to Curry, the
functional
programming
logic
system?
language. Yeah.
Yeah, great. Thanks.
Right, we have a question down here.
So it's a very basic question. So in term writing, there are theorems saying that if you want to show the union of two term writing systems terminating, you just show each of them terminating and each of them are commuting. And do you consider this?
That sounds interesting. That sounds very useful. Yeah, I think that might be another way to get the result that I presently have. I think the goal that I'm shooting for, because there's more interaction between the two, the goal that I'm reaching for where this comes from one term system and the let comes from another term system, and we have both together in one rule, I think we'll get, will be an obstacle for using that.
I see. Thank you.
That's good. Thanks.
All right, any further questions? Okay, I have a question. So you keep saying algebraic effects. How crucial is the algebraicity? Do you actually use it? Could you maybe comment a bit more on? Oh, sorry.
I don't necessarily know exactly what you mean by algebraicity.
I think so. Yeah.
Right.
I think you described it right on that slide.
Basically, this rule.
This rule, yeah.
Well, that's the one ingredient that's new.
Right.
So other work has shown that rewrite systems given these other three ingredients will terminate. And this one, yeah, it doesn't seem very problematic. Well, let me clarify that a little bit, because the Lindley-Stark uses this rule, right? But it doesn't have this rule, whereas algebraic effects like Plotkin and Power has this rule, but it doesn't talk about the effects rewriting as such. They have equations, but they don't talk about the theory of how do you decide whether it's decidable, whether it's terminating.
Right.
I'm not sure if that answers the question.
No, that's my question. Yeah. You mentioned simple types right here.
Yeah.
Yes. What about effect types? Do they have a place here? Have you?
What do you mean by
Like,
effect
do you have an
types?
effect system? Basically, that's the question. Are you tracking?
I see, where you would actually track the effects
Are you
over the arrows.
So you're not doing that, I suppose.
I haven't really thought about that.
No.
I don't
Okay.
see any reason why it wouldn't be attachable.
Right.
But I haven't thought about it.
And then I had another sort of question you mentioned in that SAM system here. We're proving normalization up to these rules, but then you add this in. Do you have the proof done when you add the fourth rule in, or
Proof what?
the proof that the system is still normalizing, strongly normalizing?
You mean if you just add this without any rewrites between the effects?
Yeah. So when you add this to your system, as it is here.
I mean, you have some proof obligation there, but it's pretty trivial,
Okay. So
I think.
you haven't. Okay. That's
Yeah.
just my question. If you've done that yet.
Yeah.
Okay. Yes. I don't have any further questions. Any last comments? Yes. Ohad.
Sorry for being a bit ignorant. Do you remember how Okada proved his result?
Yeah, it's a very short paper. It's like 4 pages. And it doesn't allude to any earlier framework, really. It's a series of steps that you can follow that seem logical. I don't know how to explain it. It sort of constructs sort of like, it separates out parts of the term to focus attention on different parts of the term, and it says, well, this part does this under this rule, and so on. It would be neat to give a little talk on that, because I think it's a pretty cool result, very old and quite straightforward. And the steps themselves, you just have to kind of read through the steps, and you go, that makes sense, that makes sense.
I know Okada has this more powerful work on ordinal diagrams in inherit from Takeuchi, but he's not using those insights at all.
I haven't read anything else by him.
Okay.
Yeah, so I've seen the name in a couple places, but I haven't read any other papers. Yeah.
All right. I think that might be it. Okay. Let's thank the speaker.
Thanks so much.